So here's another example that involves a dependent current source, which you see right here. And we're asked a couple of questions about that. The first question is, what type of controlled source do we have here? So it's a current source, but it's controlled, we see here, by this voltage V2. So for part A, then we would call this a voltage controlled current source. Or you may see that abbreviated as VCCS. So it's a voltage controlled current source. So now the second part of this exercise, they want us to determine what the total of resistance is that appears between these two terminals. So in other words, it'd be the R equivalent looking into here. So if we were to put an ohm meter on there, what would we measure? So this can be a little bit tricky, but let's take a look at how this works. So the first thing we want to notice is this resistor right here. And from that, we see that we have this current that's already defined for us right here, this I. And so from that, we should be able to see then that V2, this is just Ohm's law, V2, V equals IR, is equal to I times the resistance, which is 8. So this also tells us that I is equal to, and this is solving for I, V2 over 8. Okay, so we'll put that in our pocket and keep that for just a second. So now we want to take a look at this resistor right here, the 12 ohm resistor. And from that, we see that the voltage of the 12 ohm resistor is just 12 times I. But we have an expression for I right here, so we can plug that into this. And when we do, we get that voltage V12 is equal to 12 times V2 over 8. And so that's equal to 1.5 V2. All right, so now we have expressions for the voltage drop across both those resistors. So the next thing we need to notice is between this node and this node, these two resistors in parallel should have the same voltage drop as our current source because they're in parallel with it. So that's important because then we can determine what the voltage drop is across our current source. So let's look at that. So the voltage drop across our current source should be the same as the voltage drop across the 12 ohm and the 8 ohm resistor. Well, we know the 12 ohm resistor, the voltage drop is 1.5 V2, and we know the 8 ohm is just V2, so plus V2. And so if we add those up, that should be 2.5 V2. So the voltage drop across our current source is 2.5 times the V2 voltage, if we want to call that the output voltage. So now, again, using Ohm's law, we can solve for the R here, and we know that R is equal to V over I. Well, we know the voltage across our current source, and we know the expression for what the current is right here, so we can plug all that in. So the voltage is 2.5 V2, And the current, which is defined right here, is V2 over 4. So the V2s should cancel out. The 4 in the denominator will move up to the numerator here, so it's 2.5 times 4, and that is 10 ohms. So one thing we have to be aware of, though, here is that our current source is feeding current into the same node as the positive terminal, or what we're defining as positive. So that being the case, this resistance has to be what we call a negative resistance. So instead of deterring current going into that node, it's actually pumping current into that node. So that would make it negative. So now we have everything in terms of ohms. So we should be able now to reduce this to an equivalent resistance. But before we do that, let's go back here and show what this really would be then. I think this will make things a little easier to visualize this. So now instead of having this guy here, this will all be gone. We now have this resistance. We now have this resistance, but it's a negative 10. Negative 10, there's the way it looks when we're looking in from this direction. So that being the case, let's draw a line here, and now let's start reducing our network. So the first part of this, what we did on the top, was just determining what the resistance of the apparent resistance of our current source was. So now we can move forward with just reducing the network. So the first thing we see is we just have this 12 and 8 in series, and so that means those would just reduce to a 20 ohm resistor. So let's fill that in. So we don't need this guy anymore right here. So that's gone. And this value will change. We really don't need this I either, definition. We used to use that to determine what our resistance was. Okay, so we come back here. This will be connected across, and now this is 20 ohms. Okay, so now we want to look here, and we see we have these two guys in parallel. So we know how to do that. That's going to be negative 10 in parallel with 20. And so when we do that, that's going to be negative 10 times 20 over negative 10 minus, let me rewrite this. I got it. This will just make it a little easier. Let's do it as 20 in parallel with minus 10. So now this is going to be 20 times minus 10, and then it's going to be 20 minus 10, or plus a negative 10. And so when we do that, it's negative 200 over 10, and so this is minus 20 ohms. So now the two blue ones up here can be replaced with one resistor, so let's do that. So we don't need this anymore, so this all goes away, and we just use this one resistor remaining, and its new value is going to be minus 20. So that's minus 20 ohms. So the next step, we see that we have these three resistors in series, and so that would just be 4 minus 20 plus 6, and that gives us a minus 10 ohms. So we can replace those guys with minus 10 ohms. So let's do that. So again, all of this goes away. All of this goes away. And we're just left with this one. And so now let me fill that in. So now this is minus 10 ohms here. And so finally, we have this resistor and this resistor in parallel. So let's do that here. And so that's going to be 2 in parallel with negative 10. And so when we do that, that's going to be 2 times negative 10 over 2 minus 10. And so that will give us minus 20 over minus 8. And the negatives cancel out, and we're left with a 2.5 ohms. 2.5 ohms. So in other words, this equivalent resistance, or if we were to put a ohm meter across these two terminals here, we should measure 2.5 ohms.